Children, I hope you have gone through my previous videos and done all the work that was assigned to you. Let us now proceed further. Today we are going to start a new chapter, that is D and F block elements. Now we start with the D block elements. They are also called as the transition elements. The elements of group from 3 to 12 in the long form periodic table, they are called as transition elements, and they lie between the S and the P block elements in the long form periodic table. They are called D elements, D block elements, because they have incomplete 3D, 4D, 5D and 6D subshells. The general electronic configuration is N-1, D1 to 10, NS 1 to 2, where N is the outermost shell. In the periodic table, there are 4 transition series of elements. First series is of 3D series consisting of 10 elements of the 4th period corresponding to 3D orbitals. Second series is 4D series consisting of 10 elements of 5th period corresponding to 4D orbitals. Third series is 5D series, which consists of 10 elements of 6th period equivalent to filling of 5D orbitals. And the fourth series is 6D series, filling of 6D sublevels starting with actinium, followed by elements with the atomic number 104 onwards. So in the transition elements, the valence electrons are present in the outermost shell as well as the d orbital, that is the penultimate shell, d orbital. Okay. So transition elements can also be defined as elements whose atoms in ground state in one of the most common oxidation state has incomplete d subshell. That means maximum 10 electrons can come in d orbital, so it has 1 to 9 electrons in d subshell. It has to be incomplete. Then they will be called transition elements. There are of course some exceptions. Chemistry is full of exceptions. So exceptions are zinc, cadmium and mercury. They have completely filled d subshell in their atomic state or common oxidation state. Now let's come to the general properties of transition elements. First is the metallic character. All transition elements are metal except mercury. They are all hard, malleable, ductile. They have HCP, FCC or BCC structure. Covalent and metallic bonding both are present in atoms. The presence of incomplete d orbital, it allows covalent bonding to take place, and they are all good conductors of heat and electricity. Now next property is atomic and ionic radii. So generally the atomic radii of d block element decreases with increase in atomic number from left to right in the period. Why? Because there is an increase in the nuclear charge which attracts the electron cloud towards the nucleus. So atomic radii for elements from chromium to copper are very close to one another. This is due to the fact that addition of electrons to 3D level, it causes a reverse effect by screening the outer 4s electrons from the inward pull of the nucleus. So due to screening effect, the 4s electrons, they are not attracted towards the nucleus. As a result of these two opposing effects, the atomic radii does not differ much on moving from chromium to copper. See, screening effect you can understand like this. In a class, when there are fewer students, each and every child is under the observation of the teacher. But if the class is full of students, too many students, then the children at the back are screened by the children in the front, and teacher is unable to see them clearly. So they get away with a lot of things. So that is what is called, and that's why we have so many backbenchers. So that is what is the screening effect. When there are a number of electrons in between the outermost electron and the nucleus, then the outermost electron is shielded or screened by the inner electrons. So at the end of the period, there is a slight increase in atomic radii due to increased electron-electron repulsions on addition of electron in the same orbital, with respect to increased attractive force due to nuclear charge. So this causes an expansion of the electron cloud, and the atomic radius towards the end increases. Down the group, atomic radius increases, but atomic radii of elements of second and third transition elements are almost the same, and this is due to lanthanoid contraction. Then we come to ionic radii. Ionic radii of M2 plus and M3 plus ions follow the same trend as the atomic radius. That means trivalent and divalent ions of all the transition elements, they follow the same trend as atomic radii. Ionic radii decreases with increase in oxidation state. The ionic size of trivalent ion are smaller than those of divalent. Ionic radii of transition metals are smaller than those of the representative elements in the same group. Next is melting point and boiling point. They have very high melting and boiling point. The melting point increases due to maximum and then decreases as the atomic number increases. Manganese and technetium have abnormally low melting points. Strong metallic bonds between atoms of these elements are responsible for high melting and boiling point. So they have high enthalpy of atomization. Strength of metallic bond depends upon the number of unpaired d electron. Greater the number of unpaired electrons, stronger is the metallic bonding. So these elements have high melting and boiling points. Melting point decreases after middle because of increasing pairing of electrons. Tungsten has the highest melting point among the d block elements. Next is ionization energy or enthalpy. First, ionization energy of transition element lies between S and p block elements due to shielding effect and increasing nuclear charge. So there is a slow increase in ionization potential on moving in period. Therefore, values of the first 3D block elements differ only slightly from one another. Value of iron, cobalt, nickel and copper are close to one another, almost the same. Value of zinc, cadmium and mercury is considerably higher due to extra stability of 3D10 level, which is completely filled. So in general, you can say that the second and third ionization enthalpies increase along a period, but there are a few exceptions. For example, second ionization energy from chromium to manganese and from copper to zinc, as they acquire stable configuration after removal of the first electron decreases. Okay, so once they lose one electron, their configuration becomes stable, so the ionization energy decreases. Now, third ionization energy of manganese is high because third electron has to be removed from a stable half-filled 3D orbital. Third ionization enthalpy of copper, nickel and zinc are also very high. First ionization energy of 5D elements are higher as compared to 3D and 4D elements due to weak shielding effect of nucleus by 4F in 5D elements. So the influence of greater effective nuclear charge increases. So this is about the ionization energy. Next we come to oxidation state. Transition elements, they show variable oxidation state. This is due to 3D, 4D and 5D orbitals. This energy level is very close to 4s, 5s and 6s orbitals, and therefore in addition to ns electrons, variable number of n-1 d electrons are also lost to show variable oxidation state. Now, for oxidation state, the most common oxidation state of first transition series is 3d electrons, is +2, except scandium, which shows +3. Most ionic bonds are formed in +2 and +3 oxidation states. Covalent bonds are formed in compounds of higher oxidation state because of sharing of d electrons. Elements showing maximum oxidation states are present in or near the middle of the series. For example, manganese, it shows oxidation state from +2 to +7. Its highest oxidation state is +7. Highest oxidation state of +8 is shown by osmium or ruthenium. The various oxidation states of transition element is due to incomplete d orbitals. Alright, in group 6 elements, higher oxidation states are more stable. For example, molybdenum and chromium, they all have stable oxidation states. Next is the nature of solvent also affects the stability of an element in a particular oxidation state. Like Cu plus is unstable in water, but Cu2 plus is stable in water. Fe2 plus is unstable in aerated water. Alright, the relative stabilities of a particular element in different oxidation state can be known from their electrode potential value. Cu plus has electrode E0 value 0.52 volts. Cu2 plus has E0 is equal to 0.34 volt. The Cu plus is reduced more easily. Hence, it is less stable than Cu2 plus. Now, the compounds of metals with high electronegativity, negative elements like fluorine and oxygen, exhibit higher oxidation states. In going down a subgroup, stability of higher oxidation state increases while that of lower oxidation state decreases. Low oxidation states are found when a complex compound has ligands capable of pi acceptor character in addition to sigma bonding, like NiCO4 or FeCO5. Alright, next is colored ions. Most transition metal compounds, either in solid form or in solution form, are colored, unlike the compounds of S and P block elements. The color of compounds of transition metal is due to presence of incomplete d subshell. When anions or ligands approach the transition metal ion, their d orbitals split into different energy levels known as crystal field splitting. In case of transition metal ion, electrons can be promoted from lower energy to higher energy level with same d subshell by absorbing the light of a particular wavelength in the region of visible light. So they appeared colored due to emission of the remainder as colored light. The observed color of a substance is always complementary color of the color which is absorbed by the substance. That's just like when we see the color, we see the complementary color. Now, the color of transition metal complex is dependent on different energy difference of 2d levels, which in turn depends on the nature of ligand and the type of complex formed. Now, next is formation of complexes. Transition elements, they have tendency to form coordination compound due to small size of metal ion, high nuclear charge, and availability of vacant d orbitals. Okay. Now, just a minute. Where is the cursor? 1 minute. Next is alloy formation. Alloys are homogeneous solid solutions of two or more metals. Okay, so they are formed by metals whose atomic radii differ from each other. Due to similar in size, the atoms of one metal of transition element can easily replace the other in crystal size. Alloys are hard and they have high melting point and they are resistant to corrosion. Example, ferrous alloy. Then next we come to magnetic properties of transition metals. So most of the compounds are paramagnetic in nature. They are attracted by the magnetic field. Now you know already that paramagnetic is due to presence of unpaired electrons in the n-1 d orbitals. The magnetic character is expressed in terms of magnetic moment, which is given by mu is equal to under root n into n plus 2 bm. That is never asked, but you should know this, ki the magnetic property is paramagnetic. Now next is catalytic processes. Catalytic processes में the transition elements, because of the presence of vacant d orbitals, they can accept electrons from reactant atoms and form intermediate compounds which provide low energy path for the reaction. Certain metal compounds, they provide low energy path for reaction by change of oxidation states, like vanadium can change from +5 to +4 during oxidation of SO2 to SO3. So these are the various properties of transition elements or d block elements. Now next we have to study a compound that is, I'm sure you are familiar with this. This is potassium permanganate, KMnO4. Now first thing about KMnO4, let us study the preparation. It is prepared or extracted from a mineral called pyrolusite. Now this pyrolusite, the formula is MnO2. And this involves two steps. First is conversion of MnO2 into potassium manganate. Potassium manganate formula is K2MnO4. Now the finally powdered pyrolusite ore is fused with KOH or K2CO3 in presence of oxygen, alright, or an oxidizing agent like KNO3. So the reaction that takes place here is 2MnO2 plus 4KOH plus O2. On heating it gives 2K2MnO4 plus 2H2O. Similarly, MnO2 plus 2KOH plus KNO3 on heating gives K2MnO4 plus KNO2 plus H2. Any one of these reactions can be used for converting potassium, for converting manganate into potassium manganate. Alright, the second step that is involved is oxidation of potassium manganate to potassium permanganate. Now this can be carried out either by a chemical process or chemical oxidation or by electrolytic oxidation. So in chemical oxidation, the fused mass after extracting with water is filtered and it is converted into potassium permanganate by bubbling carbon dioxide, chlorine or ozone into the solution. So 3K2MnO4 plus 2CO2 gives 2KMnO4 plus MnO2 plus 2K2CO3. Similarly, if instead of CO2 you use Cl2, the reaction will become 2K2MnO4 plus Cl2 gives you 2KMnO4 plus 2KCl. If you use ozone, the reaction becomes 2K2MnO4 plus H2O plus O3 gives 2KMnO4 plus 2KOH plus O2. These are the chemical ways in which potassium manganate can be converted to potassium permanganate. The next method is electrolytic method, electrolytic oxidation. It is the preferred method. In this, alkaline potassium manganate solution is electrolyzed between iron electrodes. So KMnO4 to K2MnO4 gives 2K plus MnO4 minus, and water it gets electrolyzed into H plus OH minus. At anode, the reaction which takes place is green colored MnO4 2 minus gets converted to purple color MnO4 minus plus electron, and at cathode this electron is accepted by H plus ion to give you H, and 2H combined to give you H2. So at the end of the reaction, the solution is filtered and evaporated under controlled condition to get crystals of potassium permanganate. So this is the electrolytic oxidation. This is the way in which potassium permanganate is produced from the ore pyrolusite. Now in the laboratory, the method of preparation is different. In laboratory, 2Mn2 plus is reacted with peroxo disulfate ion, S2O8 2 minus ion, plus water, 8H2O. It gives you 2MnO4 minus plus 10SO4 2 minus plus 16H plus. Okay, so these are the two methods of preparation of potassium permanganate. Next we come to the properties of potassium permanganate. Potassium permanganate, it is dark violet crystalline solid having metallic luster. Its melting point is 523 Kelvin. It is fairly soluble in water to form a purple colored solution, and next property is action with concentrated H2SO4 with cold and concentrated H2SO4. It gives Mn2O7, which on warming decomposes to MnO2. The reaction involved is here. 2KMnO4 plus 2H2SO4 gives you Mn2O7 plus 2KHSO4 plus H2O. This Mn2O7, two molecules, on heating they give you 4MnO2 plus 3 oxygen. This is the reaction with cold H2SO4. Now with the warm and concentrated H2SO4, it gives oxygen. The reaction is 4KMnO4 plus 6H2SO4. On warming, it gives you 2K2SO4 plus 4MnSO4 plus 6H2O plus SO2. This is with warm H2SO4. 4KMnO4 plus 6H2SO4 on warming gives you 2K2SO4 plus 4MnSO4 plus 6H2O plus SO2. So this is the action with water. Next property is oxidizing property. Now it is a powerful oxidizing agent, and it reacts separately in neutral, alkaline and acidic medium. So in neutral medium, equivalent mass of KMnO4 is 1/3 of its molecular mass, and it oxidizes hydrogen sulfide to sulfur. So in neutral medium, the reaction is 2KMnO4 plus H2O gives you, H2O is neutral, so it gives you 2KOH plus 2MnO2 plus 3O, and it oxidizes hydrogen sulfide. So 2KMnO4 plus 3H2S, it gives you 2KOH plus 2MnO2 plus 2H2O plus 3S. Then next you come to the alkaline solution. In strongly alkaline solution, manganate ions are further reduced to MnO2. Reaction involved is 2KMnO4 plus 2KOH gives you 2K2MnO4 plus H2O plus O. And then this K2MnO4 further reacts with water, and it gives you MnO2 plus 2KOH plus O. Alright, therefore the complete reaction becomes 2KMnO4 plus H2O gives you 2MnO2 plus 2KOH plus 3O. This is the reaction. 2KMnO4 plus H2O gives you 2MnO2 plus 2KOH plus 3 nascent oxygen. Okay. Now in alkaline medium, equivalent weight of KMnO4 is same as that of the neutral medium, that is 1/3 of the molecular mass, that is 52.67. It oxidizes potassium iodide to potassium iodate. 2KMnO4 plus Ki plus H2O gives you 2MnO2 plus 2KOH plus KiO3. Now next is in acidic medium. Now in acidic medium, in presence of dilute sulfuric acid, it behaves as a strong oxidizing agent. The reaction is 2 KMNO4 plus 3 H2SO4 gives you K2SO4 plus 2 MnSO4 plus it gives you K2SO4 plus MnSO4 plus 3 H2O plus 5 nascent oxygen, and the equivalent mass of KMNO4 in acidic medium is 1/5 of its molecular mass, that is 31.6. This you have to remember. In neutral and alkaline it gives you 1/3 of its molecular mass, and in acidic medium it gives you 1/5 of its molecular mass, so the value comes to 31.6. Some oxidizing properties of KMNO4 in acidic medium is, first, it oxidizes oxalic acid to carbon dioxide. Reaction is 2 KMNO4 plus 3 H2SO4 plus 5 H2C2O4. This is oxalic acid. It gives you K2SO4 plus 2 MnSO4 plus 8 H2O plus 10 CO2. The next is, it oxidizes potassium iodide to iodine. 2 KMNO4 plus 8 H2SO4. All these reactions will take place in H2SO4. That is why it will become acidic medium. Plus 10 Ki. It will give you 6 K2SO4 plus 2 MnSO4 plus 8 H2O plus 5 I2. Then it oxidizes ferrous sulfate to ferric sulfate. Okay. So reaction is 2 KMNO4 plus 8 H2SO4 plus 10 FeSO4. It gives you K2SO4 plus 2 MnSO4 plus 5 Fe2SO4 whole thrice plus 8 H2O. So from Fe2 plus, ferrous changes to Fe3 plus. Next we come to uses of potassium permanganate. It is used in volumetric analysis for estimation of ferrous salts, oxalates, iodides and hydrogen peroxide. Alright, in titrations you will be doing them in the practicals, so you can see, and it is obviously also used for oxidizing agent because it oxidizes a number of compounds. Then it is used for detection of presence of unsaturation in organic compound in the form of Bayer's reagent. So Bayer's reagent is nothing but alkaline KMNO4. It is used as disinfectant and germicide and for purifying water. It is also used for bleaching of wool, cotton, silk, etc. Now next thing which you have to study is structure of permanganate ion. Now manganese in MnO4 minus, it undergoes sp3 hybridization, and hence the 4 oxygen atoms, they are arranged tetrahedrally. They form a tetrahedron, alright, around the manganese, and in this 3 are joined by a double bond and this one is joined by single bond, so it has a negative charge. So this is the structure of permanganate ion. The remaining part we will do in the next video.